Okay, well, thanks everyone for coming. Today we're happy to have Sid tell us about symmetry fractionalization from microscopics, which is a super exciting topic, which will probably be one of the final ones of this year. Definitely the final one before Thanksgiving. So take it away when you're ready, Sid.
Perfect. Thank you so much for letting me present, guys. So today I'm going to be talking about symmetry fractionalization, but sort of in a different, independent way from sort of the previous treatments that you might have heard, which is like more algebraic in nature. And along the way, I'm going to use this as an excuse to sort of talk about C-star algebras, which I really like, and you guys should too, I hope. Okay, so first, so these are my collaborators, Kyle and Daniel. They're both from Ohio State. Kyle is a postdoc, and Daniel is a PhD student over there. Fantastic collaborators. And yeah, we are writing a continuation of this paper, which should be done sometime soon as well. Okay, so here's the sort of outline. First, I really, this is like a physics talk. I would like to talk about the physics of it and understand what's going on before I sort of give you guys like extreme amounts of copious mathematical details. And then here I'm gonna actually switch gears and talk about operator algebras, but like in sort of in the very narrow context of anions and symmetry defects that I've sort of worked on in my PhD. And then finally, there's I'm going to talk about how to get the symmetry fractionalization data out of. So there's like two sort of ways in which you can get it. One is like the operator algebraic perspective, where you're like being extremely fussy and sort of arcane with your methods, or you can sort of be a or have a lowbrow sort of approach and try to do it like in normal physical systems. I personally like the latter approach way more because I understand what's going on. But nevertheless, like these two things are exactly the same, and I'll sort of talk about the equivalence between the two. Okay, so also during this talk, I really want to treat this talk as a pedagogical talk, especially for these two things. Okay, so at any time you have any problems, you don't understand something, just stop me, and we'll go over sort of how to think of it. Because all of these things, like C-star algebras, are sort of very physical objects, but sometimes it doesn't feel like it. So, and over the years, my intuition has sort of told me what is what. So, I can share that whenever you guys want. Okay. All right. One more caveat before we start doing this is like really, this thing is microscopics. Okay. So at any point during the talk, if you stop me and say, Sid, I don't really understand, you lost me. What is the physics? Okay. What are the observables? Like I actually have access to every single observable or every single operator in my Heisenberg picture of quantum mechanics in this talk. Okay, so I haven't lost any data. Like you give me some projection, you give me some sigma, like some Pauli operator, and you ask me what is its expectation value and things like that. All of that can be done at any point in this treatment. And that's kind of the beauty of this approach. Okay, what is a defect? You might have actually, this term is kind of overloaded in the literature. There are many kinds of defects, I suppose. There's, right. Common ones are sort of lattice disclinations. So those look like, you have some sort of, you have a lattice like this, but then let's say the lattice is sort of shifted a little bit. Like there's a small little earthquake, and that is like sort of changed the plane of the lattice, such that as you go out from one side to the other, you're going to see some sort of effects over here, something that has changed, things like that. But and this is sort of a defect or a domain wall of a translation symmetry, which is not the type of symmetry I want to talk about today. I'm just going to talk about on-site symmetry, but there are different connotations for this term. Specifically, what I want to say is that domain walls or symmetry domain walls are actually also called symmetry defects. But this time around, I'm going to sort of say like, no, a defect is a very specific thing. It's actually basically like an object, a localized sort of object where there is a domain wall on one side of this localized object, and then nothing or vacuum on the other side, or like the ground state on the other side. Right. And by the way, we're doing all of this in 2+1 dimensions. There's no, like, this is not a boundary of a 3+1 dimensional system. This is like inherently just a 2D system. Okay. So, right. So this is the picture. This is the lower. Okay. What is a symmetry defect? You have this sort of domain wall over here and nothing over here. So let's say you have an anion, A, and it goes through sort of the domain wall side of this defect. Then it's going to have some sort of action, some sort of G action. Let's say this was a G domain wall, where this anion is like acted on by some symmetry. Whatever does that mean? We don't know just yet. Okay. And then on the other side, if it goes through the vacuum set, then it's just going to be the same. It's going to stay invariant, and there's going to be nothing that happens to it. Okay. And right, so this is sort of the algebraic approach. You start from very first principles. You start off with some category of anions which has no structure, no underlying structure, in the sense that like there's really like it doesn't know anything about the underlying lattice or the underlying microscopic system. So you start from some category, and then you define some sort of G action onto that category, and then you get a G cross braided tensor category. All of this is like algebraic, and it forgets the microscopics. But and so because there's like so much forgetting involved, there's really always the question that is this treatment, though beautiful, is it correct? And what does correct mean? Well, it means that if I take some lattice model, some nice models that I know, like let's say the Toric Code or something like that, then can I actually construct the category that they construct? Does it give me the exact same category? And right, to spoil the rest of the talk, yes, indeed, you get the same category. But the process to get there is very interesting and gives rise to some very physical ways of thinking about symmetry fractionalization. Alrighty. So what's our setting? We're going to have a Hamiltonian, which I should have mentioned is gapped. Okay, it's a lattice Hamiltonian, so it's going to be some interactions which are sort of local. Think the Ising model, Toric Code, Levenman. All of these are nice Hamiltonians that fall under this class. And even more generally, like the what's the other model by Kitaev? Honeycomb model also falls in the same category, and so on and so forth. We're going to have an on-site symmetry. Now, I want to note that this on-site symmetry is sort of a crucial aspect of this treatment, because it allows us to sort of break our symmetries into sort of tensor products acting on like spatially distinct regions. So for example, if I have like some U of G, which is like a symmetry action on the entirety of the lattice, or on the entire state, then you can break it down into like two different symmetry actions acting on the left and the right sides of the lattice. So just break up your imaginary lattice, which I haven't drawn, into two, and just call one of the regions left and one of the regions right. And the symmetry will actually break up into a tensor product of these two things. So that's what it means to be on site. And this can be done for like any division of your lattice. Okay. And then finally,
Would you say that's the definition of on-site, or would you say that that's a property of being on-site?
So the definition of it's sort of interchangeable. You can you can choose one to be the property and the other to be the definition. So if you have this, then it implies that it only acts on every site as a product representation of the symmetry. So yeah, you could interchange it.
Okay.
This is maybe for 1D, right?
No, this is actually for 2D as well, like for
But just knowing that you can split left and right, like you would need compatibility of the splittings in different directions.
Right. So, but this is a tensor product. Um, um,
At least I think it's subtle. I tried to prove such things, and I couldn't do it.
well, so as long as you know that this can be done for any splitting, I think you should be okay because this is just a
In that case,
2D
yes, I agree.
lattice. Yeah, yeah.
Yeah, along any cut, right?
Yes, yes. So
Okay.
you really need any cut, okay? It's not just like for some cut or something like that.
That's
Yeah,
right. That's right.
absolutely.
Okay, I agree.
Absolutely. Okay. Yeah. Also, our Hamiltonian is going to be G-symmetric. And really what that means is like you take the whole symmetry and then you conjugate it, conjugate the Hamiltonian with the symmetry, and then you get back the Hamiltonian. Easy peasy. So this actually implies that the ground state is symmetry invariant. And good. Do we need anything else? No, not really. We don't even need the assumption that the ground state is unique. We can have like a manifold of ground states and things like that as well. Okay, good.
Wouldn't
Yes.
like the invariance of the Hamiltonian not imply invariance of the ground states? Like what if it's just spontaneously broken?
Ah, good. Yes. Yeah, so we do want to discount that class. Indeed, yes. I want to say that right, I'm not considering spontaneous symmetry breaking, meaning the ground state. Yeah, perhaps you need both of them then. Yeah, thanks for the question. Yes, I think this is only implied when the ground state is unique. But if there is a manifold of ground states, then indeed you would probably need also the fact that the ground state itself is invariant. Yeah.
Mhm.
Thanks for the question. Good. Okay. So right. So you have some symmetry U of G, and then you also have the fact that it breaks up for any sort of division of your lattice into left and right. It breaks up into tensor products of left and right. So I've just chosen the right over here. So I took some line, and then I divided the lattice into left and right regions, and I just chose like some restricted symmetry action acting along like some part of the plane. Okay, so now I want to look at states of this form. Okay, so now if notice that if let's say an operator is over here, sort of like really far away or like far away from any sort of boundary effects that might come into play, then this symmetry action, you write, basically acts as identity for such an operator, and then you get that the conjugation is equal to A. Now, if the operator is over here, then you no longer get that. But if the operator belonged to the Hamiltonian, because of the fact that the Hamiltonian is invariant, you would actually get that this operator is also invariant under the symmetry action if it lies deep in the bulk. Okay, so basically the physical picture is that in your Hamiltonian, the interaction terms that are over here have no idea that the symmetry was cut. It's just like there's no action. And then the interaction terms that are deep in the bulk of this restricted symmetry action also have no idea because they sort of have some finite range support, things like that. I should say, yeah, a operator in Hamiltonian. Of course, this is not true for general operators, right? There might be some operators that might distinguish the action of the symmetry. Like, you just take the, yeah. Yeah, so something that anti-commutes with the symmetry action and immediately it's going to diagnose something from here to here, but not in the Hamiltonian because it's symmetric. Alrighty. So what's the idea? Elsenaek was sort of the inception of this whole like class of works, at least as far as I'm aware. Please correct me if I'm wrong. The idea is sort of that you have this restricted symmetry action, and then you start to like correct that symmetry action using something that is localized along the boundary of the symmetry action. And so like I've chosen the operator F that sort of is localized literally along this blue strip, and it sort of corrects for the action of the symmetry in the sense that for the Hamiltonian terms, of course, in the sense that, if, let's say, right, so you have, right, so let's say A was in the strip. So A is like some operator that's supported over here. So note that over here, we assume that if A was here or here, then it's not going to feel the cut action. But if it was here, then it would definitely feel something, because like it can see like, oh, there's some symmetry acting over here, but nothing on the other side of my A. So it would be changed. It would not be invariant under the symmetry. But let's say we look at that same A. So if let's say A is over here, and we conjugate under the symmetry like usual, the restricted symmetry, I mean, and we conjugate under this sort of symmetry correction operator, then we should actually get that it's left fully invariant as well. And in other words, so if A in Hamiltonian, or in Hamiltonian, which is like a crude language just to say that it's an interaction, then this property will hold everywhere. So it'll hold over here, which it did before. It's going to hold over here, which it did before. But now it's also going to hold for all A operations in the Hamiltonian over here as well. So everywhere you've sort of, as far as the terms in the Hamiltonian are concerned, you've sort of erased all of the boundary action that the symmetry had. And for your purposes, like literally the symmetry is like all gone if you are in the Hamiltonian. Again, keep in mind that this is only on the level of Hamiltonian terms, and a general observable will definitely be able to distinguish between certain things. The left and the right action. Okay. Okay. So now the whole idea was that they had was that, okay, you have this correction, and in a certain sense, you sort of want to cut the correction into like some lower parts and upper parts. Keep in mind that this may not always be possible. And especially in 3+1 dimensions, there are examples where sort of, if you're looking at a 2+1 dimensional manifold, that's a boundary of a 3+1 dimensional manifold, it's not always possible to cut such an F into 2 without like seriously disrupting stuff that happens over here. But in 2+1 dimensions, in all examples that I could find, it's always possible to cut this correction operation into sort of a tensor between like the upper and the lower halves. Good, right? And so the conclusion of that paper was sort of in some dressing, of course, is that, okay, you look at this cut part of the dressing action, and that is exactly where the symmetry fractionalization data lies. Or well, so they considered the case of SPTs, but really what that treatment was saying, that like, okay, if there is some sort of projective representation that's happening of the symmetry that enables you to classify SPTs, that is going to hide where at the boundary of this cut. Okay. So, but then like sort of, I want to stress on an extension that we sort of that I didn't know before this work, and perhaps it was well known in the community before I jumped onto the ship, but I found it insightful, so I'm sharing this intuition with you guys. So let's say I have the ground state, and I have some restricted symmetry action acting on it, and some correction F. I should really say that it's F. So FD maybe. D, F prime D. So this is F prime D, and then this is FD as well, because indicating that this thing has been cut. Okay, so the idea is that, look, if you're acting on the ground state with these two operations, they really are the same operation. Like you can actually sort of, once the symmetry has been corrected for in the lower half, this actually is freely deformable as long as you're acting on the ground state. So you want to sort of think of it as like a string operator, in the sense that, like, let's say you have some string operator that's going down over here, and then you act on it with the ground state. You're actually able to freely deform that string operator as much as you want, as long as the endpoint of the string operator stays the same. So the string operator is like movable, and this is exactly what you're sort of seeing over here. You're seeing that, as long as you're acting on the ground state, this thing right here is able to be moved freely, as long as it doesn't sort of cross over to the other side. So like it's got some region where it's able to move freely. Okay, so really it's a string operator, and you should think of it this way. Okay, so that is sort of the rough intuition of like where the symmetry fractionalization data might hide, and I'm gonna sort of start to formalize this. But before that, if you guys have any questions, this is a great place to stop and righty, let's keep going. So in order to formalize this, we're going to use something called operator algebras. And this is not, it seems like a scary term, but it really isn't. It's just Heisenberg dynamics or Heisenberg picture for operators for quantum mechanics, but just like formalized so that you can handle infinities as well. Okay, so under this formalism, it doesn't really matter if your lattice is finite or infinite. It can account for both of those, and thus it gives like a very, very good, robust way of thinking about the thermodynamic limits. Okay, so this is going to be an important object in our analysis. This is called curly A. It's the algebra of observables, or in many treatments, it's called the quasi-local algebra. It's the algebra of like local operations that are like limits of basically local operators. Okay, and examples of such operators, if you have like a Hamiltonian on some finite region of the lattice, it's a part of this algebra. Any string operator is a part of this algebra as long as the string is finite. And then any symmetry action is also a part of this algebra as long as the symmetry action is on some finite region. So this B over here denotes like a finite ball of the lattice. Okay, so literally all operators with finite support are all in the quasi-local algebra. You can think of any projection, any sort of easy thing, it's all in this algebra. But nevertheless, there are things that are not in this algebra.
Wait, one thing. So does H mean like the on-site Hamiltonian, like the Hamiltonian density, or you mean?
So I really mean that, let's say H of lambda, where lambda is, or maybe I should be consistent. H of B, where B is like sort of some ball. So you think the toric code, but the ball, so the H of B will just mean all of the terms of the toric code that lie entirely in the ball or something like that.
Yeah, just some finite ball.
Exactly.
Finite number
exactly.
Yeah, makes sense.
Exactly. An important detail here that I don't really want to stress on is that you can't really have infinite Hamiltonians in this formalism. There's something called dynamics that and derivations that you need to sort of generalize to. But for our purposes, the existence of it is good enough, and we don't have to worry about any of this. Suffice it to say that quantum mechanics still works in this picture, which is good because this picture was created to handle infinite dimensional quantum mechanics. Alrighty, so what objects are not in A? So if you take the limit of the ball, some finite ball going to infinity, then your symmetry action is actually not going to be in your algebra of observables. Neither is your string operator if you go to infinity. And let's say, you have some projection, some operator that projects to the ground state space on some finite ball B. If you take this ball B to infinity, then immediately it tells you that the projection is not going to be in A. Okay. So, normal things are in A, normal things that I as a physicist would study. But when you take the things to infinity, things become weird, and you sort of, you lose certain operators in this A. Nevertheless, you can actually account for all of these things by considering sort of different variations of these well-known objects. So, right. So in order to account for like this infinite limit not existing, you actually look at endomorphisms of the quasi-local algebra. So, right. So an endomorphism is a morphism. So, it has the sort of distribution that you would expect, and it's like a normal representation of A, but onto itself. Okay. Now, let's say you're considering the symmetry action, and you really do want to like send the ball over to infinity. Then what you do is like you literally just adjoint the action of like adjoint the previous operator that I said was like not good, this operator right here. You just adjoint it onto any observable that you want, and immediately that's going to give you the symmetry action. So this is on the level of observables. So for every observable A, I can define a symmetry action on this observable, and that's sort of like that's to be contrasted with sort of the usual sort of symmetry action U of G on, let's say, the ground state, for example, or U of G on some state. That's the this is the infinite dimensional version of it. And then you also have limits of string operators. So once again, you sort of take the string operators, adjoint it onto some observable A in the quasi-local algebra, and then you send it off to infinity. Okay, so this will give you basically a string operator that's really sort of one end of the string operator is really far away. So something like this, and then this is like all the way off to infinity, and all of these things will converge. They have a nice limit, and that is why we study them. That's kind of the point of defining these endomorphisms. Alrighty. Anyons. Okay, so that last example in particular is a very important endomorphism that sort of we consider. It's localized and it's transportable. So what does that mean? Let's say if I have, right, so let's go back to this definition. We have some observable A, okay? And then this thing is acting on A by adjointing with some string operator. Okay, and let's say the string, this gamma n, lies in some cone lambda. Okay, so if I'm looking at observables that are outside the cone lambda, then the string operator is just going to commute, right? And the adjoint action is going to be on just nothing, and it's going to annihilate itself. And therefore, for any observable that's like outside this cone, this adjoint action of the string operator is going to do nothing. Okay, just usual commutation relations. And that's why we say that, okay, well, this endomorphism is localized inside cone lambda. And it's also transportable. And transportable really just means that, okay, if I have something that's localized in some cone, there for any other chosen cone, let's say if I choose this cone, then there always exists something else. Let's say over here, there's a sigma right here. There exists something else that is localized in that other chosen cone and is actually is isomorphic to our previous endomorphism. So that's what it means to be transportable. Of course, these have like extremely sort of physical meanings, and I think the next thing is, or maybe in the slide after, I actually say what the physical meaning is. Okay. So right. So this string operator is actually localized and it's transportable. And these are sort of the correct endomorphisms to think about for anions. Sort of you can see why. It's a string operator that's sort of going off to infinity, and it's like sort of kind of localized in a cone. So, you know, these are the sort of objects that we want to consider. Right. If you don't like endomorphisms for some reason, which is fine, you know, not everyone appreciates mathematical details. You can sort of just think of it as a really long string operator. Okay. Adjointing with a really long string operator will give you some endomorphism. And right. So over here, let's say you have some really long thing, like some limit that doesn't exist, but let's say it does. And you just adjointing, you're conjugating your observable with that. Okay, so it's just normal stuff, but sort of encoded in a slightly arcane way. Good. Okay. So right. So here's the physical interpretation for what locality and transportability mean. Locality means that the string operator, or some more complicated object that might have resulted in the anion, it lies inside some cone. And transportability just says the sort of the similar thing that I touched on, is that if I take the expectations under this conjugation, then as long as sort of, maybe I should redraw this diagram slightly. Let's say I have two different string operators, okay? I have, let's say, f gamma over here and f gamma prime over here. Okay, so if these two string operators truly have the same starting point, then actually it turns out that the expectation of this conjugation on some ground state is going to be equal for both of these, okay? Because the string operators can be moved. This thing can be moved to this other thing. And that's kind of exactly what transportability is saying, just on a level of C-star algebras. And there's an isomorphism over here instead of equality because, well, you don't have the expectation value with the ground state. So you need something else, some isomorphism that takes you from here to here. And that isomorphism that morphism is actually an isomorphism. Okay. Right. So that's sort of what is a localized transportable endomorphism of a quasi-local algebra. And now let's categorify sort of these localized transportable endomorphisms in the sense that we're going to imbue some tensor category structure on them. So let's call the category of localized transportable endomorphisms as DHR. Okay. The objects are, well, localized transportable endomorphisms, and it's a linear category. It's got sort of some intertwiners. So if you look back at this picture right here, then notice that, in order to get from this string operator to this string operator, what you have to do is like you sort of have to like go here and then go here and then go here. So if I have like such a pizza operator going off to infinity in such a way, then if I conjugate that, or if I multiply this operator with that pizza operator, then I'm going to get back this operator right here. So, right. And so that pizza operator is an example of what is called an intertwiner, some unitary thing, or it doesn't necessarily have to be unitary, but in this case, the pizza operator is that relates relates any two endomorphisms in this category. That's the space of intertwiners. There are many such pizza operators for any two things, but that's an example. There's also fusion of endomorphisms. So fusion is just composition of endomorphisms. And notice that like usually you think of anions being fused as like a spatial fusion. You take some anion over here, you take some anion over here, and then your fusion is sort of saying that, okay, you're going to bring them close enough, and then only consider some region that's like that's outside where these two anions lie. So there's like some spatial notion of separation or like lack thereof, and like closeness and all of that. Over here, none of that. Okay. Our fusion is actually temporal fusion. You can sort of think of this fusion as like, okay, I take this anion rho 2 first, and then I apply the anion rho 1. So you can literally have two anions sitting on top of each other, and they can also be fused. So, right. So if you think of it as like let's say this is the time direction over here. And let's say I have some anion A over here in some lattice over here. And then I can also have another anion B. So I guess this is anion 2 and this is anion 1. And I can sort of compose them or I'm composing them in a temporal way when I call it fusion. Okay, good. And so, right, so this sort of fusion is also like exactly the same as spatial fusion, just like turned around just a little bit. Good. Okay. And then there's also braiding, where you sort of take two anions and then you flip them up. So you just like take one and then switch it. Okay. So with sort of the fusion and the braiding structures, turns out that the category of localized endomorphisms, localized transportable endomorphisms, is actually a C-star tensor category, or braided C-star tensor category. If this doesn't mean anything to you, that's fine. It's just a braided tensor category, which is great, because sort of you would have expected that the category of anions is a braided tensor category. And then there's like some sort of additional assumptions that are required, like the existence of some gap, something like that. And this category has been sort of verified to match the well-known categories that exist in literature. So in particular, so the Toric Code category, the quantum double category, and the double semyon category is the exact same as the DHR category of these models.
Can I ask a question about this theorem?
Yeah, what's up?
So, I mean, these objects have been around for a long time now, but this theorem, I guess, is pretty recent, right? So what are like, is there like a new technical tool that was developed that allowed this proof? Like, why didn't we have something like this like long ago? Or was it just the definition of DHR?
So I actually want to contrast this by saying that we actually do have this from long ago. There is this whole branch of axiomatic QFT. But all of those treatments, I'm not too familiar with this literature, but in all of these treatments, sort of similar ideas were used, but never like the category theoretic descriptor was not very explicit in those treatments. But I think it was all there long ago as well. But these were all like sort of just QFT notions that some researchers came around and like took to the lattice and proved it in the lattice. And that is where sort of the real genius of this theorem lies, is that like they took all of these relativistic approaches that were really nice and really theoretical and made it and translated it onto the lattice, which is not relativistic, and used like these things called Lieb-Robinson bounds and things like that.
But people were doing that for a long time too, right? That's also very old. And maybe you would argue that most of this stuff comes from the lattice anyway, because they started by thinking about like lattice QFT. But I just wonder, like, did nobody ever ask this question of like, how do you get the braided category from the anion model? I mean, it seems like a pretty obvious question.
Certainly on the lattice, So, okay, one thing I want to say on the lattice, right? Because I'm only really aware of the literature on the lattice, like very well, I suppose, is that nobody really knew what an anion was on a lattice. Like a rigorous definition was never really proposed until Peter Nikens came along in 2011, I believe. And he was like, okay, well, you
But is that
consider
true? Like,
so,
isn't the definitions in Kitaev are also rigorous, right?
well, a global anion is different from a local anion. So like, so Kitaev had the definition of an anion, which is like the totally like sort of the correct definition if you're looking at microscopics. But sort of to find a global anion, so just to sort of impress upon you the difficulty of what goes wrong in the infinite volume is the following. Okay, so let's say you define some anion as some localized transportable quasi-particle. So you have some anion over here, some anion over here, some anion over here, and so on and so forth. And let's say you try to define it via projections. Okay, you try to say that, okay, well, if I project over here, it's going to tell me that there is some anion inside this region. Here, it's going to tell me there's some other anion, and so on and so forth. There could always be another anion lurking right, sort of right around the corner, like just away from some finite projection, right? So you really need limits of projections in order to understand what is the global behavior, what is the global boundary condition, if you will, of these anions. But to find such a projection and to actually take proper consistent limits of it is just not so easy. And so what Peter Nikens and Ogata did, well, Peter Nikens did and then Ogata translated, was that they looked at representations of C-star algebras, and then they did the whole super selection sector stuff, which was.
I guess what I don't really understand is like, everything was working in finite volume. Lieb Robinson works in finite volume. You can do Hastings, adiabatic continuation. Like everything is rigorous.
Right.
It's just not phrased in terms of infinite volume. So, and I think that's almost better. So was it what people just did, like just figuring out the infinite volume limit?
Right. So, okay, in finite volume, the thing is that you don't truly have topological order. Okay, everything is related to
Maybe I've
everything
derailed you
else.
too long,
Yeah.
so we can talk about it later.
Yeah, absolutely. But right, so yeah, for infinite volume, the problem is that like really, if you start to think about topological order in sort of like an RG flow type way, there's just really no good way of thinking about it. Like there's no super selection sectors. There's nothing interesting that happens in the C-star algebra level. And you would say sort of that, that maybe like that's fine that the thermodynamic limit sort of exists anyway. But sort of how do you know? How do you know that your limits of finite lattices going to infinite volume are still going to retain the exact same anion content? Because you don't have any way of verifying the infinite dimensional counterpart of it. But okay, so let's maybe talk about it after the seminar. Thanks for the question, though. It's a very interesting, like, why didn't anyone do this? It seems simple, but I do want to say that there are some very interesting techniques involved in that result. I would not call it a trivial result at all. Okay, so what is a defect? Let's sort of re-examine that question. So earlier there was that picture where, okay, you have some anion, it's going here, you get some symmetry action, and if it's over here, if it follows this path, then nothing happens to it, and then this is the sort of symmetry domain wall. Let's consider sort of the bracket gamma 0 to be the set of all paths that are basically gamma 0 under infinite limits. Okay, so I'm thinking like something like this, something like this, something like this. All of these are paths that are in this equivalence class of gamma 0. And that is to say that like I can actually move this localized symmetry defect around in like any finite capacity, and it's still going to be sort of a symmetry defect. I just won't be able to move it infinitely.
Do you have to then, so that basically means you have to preserve the behavior of gamma 0 at infinity?
Exactly.
So
right.
instead of being like, homology classes, is it some sort of relative homology that classifies?
Exactly.
I see.
Exactly. And the relativity will be determined by what exactly is the behavior at infinity. It's just, right. So there's this thing called point at infinity. So you take some sort of boundary circle and you take infinite limits, and you're gonna get, you sort of, you take paths that have a unique point at infinity. There's just a whole host of technical things that that we talk about in the paper, but right, the idea is that yes, there is some infinity behavior that is going to dictate your cohomology classification and things like that. Absolutely. Okay, good. So now that we have sort of our definitions of what exactly is an anion, we can actually start talking about what we could rigorously say is a symmetry defect. Okay, so here's some cartoon. So let's say I have this like previous sort of cartoon of a symmetry defect. So it's like this thing where like you have a domain wall over here, and now it's been corrected in some sense. So you can, right, you can move this around however you wish. So you take some anion supported on gamma, and you sort of like take it through, and then you push it through inside from sort of inside the domain wall. Okay, so there's like some sort of bubble that can form that envelops the anion as it's entering. So as it's entering, you can think of it as like the domain wall deforming a little bit more, and then like as the anion is far enough away, it sort of closes in on itself. And since G is invertible, you always have sort of just a bubble. There's no like boundary effects that's sort of keeping this bubble close to this domain wall. So you have this bubble on this anion, and then you can like sort of remove the action of the bubble and consider that as the symmetry action that is happening on the anion. Alternatively, what you could do is like you could take the anion and push it through the other way. Okay, so you could take it. Let's say you don't even push it through. You literally just like move it over here, and then you sort of move this blue region over here because it's sort of symmetry corrected, and so it's like invisible, and it's almost like a string operator, and so I can move it freely. And in this case, I sort of move it on top, and it leaves no signatures because sort of this is like a string operator that this thing does not talk to. It's been corrected for. As far as this anion is concerned, because this thing has been corrected, this anion is never going to see what this blue line is. It's just nothing for it. Okay, so these two ways of sort of moving an anion into the bulk of the symmetry action sort of are exactly the rigorous ways of thinking about what is a symmetry defect. So if you go from one side, there's some symmetry action. If you go from the other side, then there is no action, right? And that's exactly what we wanted. But sort of it's not a reductive definition in the sense that you're not doing it in the sense that like, okay, there is something and then you push it over here, then you have blah, you push it over here, you have blah. You're actually sort of adding this symmetry action on top. So it's an additive sort of definition, and then trying to erase like half of the symmetry or half of the boundary of the symmetry so that you really get something that is like something like a domain wall. So rather than thinking about a domain wall as like cutting a symmetry open, I would like to think of it as correcting asymmetry on the other half of the the completion of that half infinite line. Okay, so what is a rigorous definition of a symmetry defect in terms of endomorphisms? Okay, so earlier we sort of touched upon the fact that an anion is a localized transportable endomorphism. So it's an endomorphism that has some localization property, and then you have some transportability as well. But over here, sort of looking at what's going on, let's say I have some cone lambda over here. Just for the sake of simplicity, let's say the path lies inside lambda, but it works for every other thing as well. You have sort of two regions, okay? You have region 1 where there is no symmetry action, and you have region 2 where there is a symmetry action as long as you're looking outside the cone lambda. So notice over here for a cone like this, you have like this region which is symmetry action, and then you have this region which is no symmetry action, something like that. So right, so remember that, recall that if, let's say, you had an anion that was localized in some cone lambda, then it would basically not see anything outside of lambda. Okay, so observables outside of lambda would just act on as identity. But over here, something weird is happening. It's actually not just acting as identity. It is for all the Hamiltonian terms, but let's say if there is a general observable, it's not going to act exactly as identity. It's going to have some sort of symmetry action. Okay, so if you have an observable in region 1 outside lambda, then there's no symmetry action here, and the endomorphism is literally just going to act on the observable as an identity. And then over here in region 2, if the observable is in region 2, then the endomorphism acts as a symmetry action. So something or nothing over here, and then some symmetry action over here. So basically, for every time you sort of like define this gamma 0, what you're doing is like you're assigning a clockwise direction to the plane, something like this, that starts off at gamma 0, and then you say that, okay, so you have some region of the clock where there is nothing, or like some hours of the anti-clock, I suppose, which has no symmetry action. Then there is a region that you don't think about where there could be an anion lying inside, and then there is some region where there is a symmetry. So it's like sort of right. So that's sort of what would mean what a symmetry defect would be. So over here, like I'm really like in this picture, I'm really thinking that secretly, there exists some symmetry correction over here that is existing in this cone in sort of this way. So I'm considering that secretly this thing right here was inside the cone, but I chose not to think about it, and I was just looking at observables outside. Okay, so in the case that the endomorphism does precisely this thing, meaning it acts as nothing over here and as G action over here, then you say that it's G localized instead of like purely localized. Think about it as like, okay, if G is equal to 1, then it literally is doing nothing anywhere, right? So it's truly localized. But when G is not equal to 1, then it's sort of doing something. And that's what G localization means here. And then transportability means exactly the same thing, in the sense that if you choose a different cone, so let's say you choose a different cone, lambda prime or something like that over here, then there exists something else that is hidden away in lambda, like this. So something like that. And then there's still like some symmetry thing going on over here. That is actually equivalent, isomorphic to the previous lambda that we had. So that look kind of like this. So it's kind of like the usual notion of transportable, but you have just G localized tacked on at the end. Okay. Oops. Okay, so right. Have I lost everyone in the audience yet?
Nope.
Well, that is disappointing. usually at this point, I see most of the people in the audience are like twiddling their thumbs, and I'm like, okay, let's talk more physics. But okay, we're going to continue with math. Okay, so let's define our category to be GSEC G gamma 0. So this is the relative sort of classification that Omar was talking about. This object is also going to be an input in our category. And this G is an input because it's a G localized object that we're thinking about. Okay, so now I can define the main category, the GSEC gamma 0, which is just a direct sum of all of these different G components over all G and G in the group G. And notice that there is an obvious grading over here, and that is the G grading, because every component is sort of distinct from every other component because of how this action right here is different for every component, and there are necessarily no intertwiners between two components that have different group elements. Fusion is the exact same. You have endomorphisms before, so you can just compose them, easy peasy. Okay. And then I've noticed that if G is equal to 1, then this definition literally reduces to localized transportable, which is great because that's exactly sort of what you expected, right? Like if a G equals 1 defect is present, then that basically means that the domain wall is doing nothing. There's no action to the anion. So there's literally nothing, and the anion would not feel anything. And so this is very reassuring that this is the case. And in BBCW, they have this thing called C0, which is the 0th component of your G graded category. That is just the set of original anions that you started off with. So good. So this is a complete sort of superset of the usual anion definition. So this category has all anions as well as all symmetry defects, and also all combinations of those two. So you have a symmetry defect and an anion, and you just like compose them. That's also in this object, in this category. Oh, maybe that last point deserves a little bit of explanation. So let's say you had an anion hiding over here. Yeah, it's possible, right? Such an object would also satisfy G localization. And therefore, obviously, every time you have a symmetry defect, you probably also have some anion also hiding away. And those two things, like the combination of a symmetry defect and an anion, is also an object in this category. Okay, so we've talked about G grading. Now we're going to talk about G crossing. So that basically means that there is some symmetry action that's happening on our anions. So it's unfortunate, but it's just life, that every time you go up a level, if every time you go up, say from states to operators to endomorphisms, the actions always like increase multiple times. So, the symmetry action on a state is U of G, but the symmetry action on A is beta G, which is conjugation by U of G. And then the symmetry action on rho is actually conjugation by beta G. So it's just a fact of life that every level you go up, you have more conjugations, more and more and more. And over here, because we are on the 3rd level, we are on endomorphisms, or 2nd level, depending on how you want to think about it. The G crossing is just given by a conjugation by the symmetry action that you had earlier. And like, this is nothing complicated, okay? This is literally, if you want to be lowbrow, that is totally fine. And we sort of think of this gamma G on rho as sort of just a fancy way of saying you have a string operator and you acted on it with a symmetry. Easy peasy, right? Nothing fancy about it. So this G crossing is the reason why we call it G crossing is because there is some G component over here on this gamma. And let's say if rho was an object in the H component of the category, then the resulting object is actually going to be in a different component. So there is some crossing going on. So you have a conjugation by some group element G. So this new object is going to be somewhere else, which is totally consistent, by the way, with our usual idea of what a symmetry defect should be. So let's say if there's a G defect, then let's say there's an H defect, and I act on it with a symmetry everywhere, then that H defect will go into G at G inverse defect. So good. We have the proper G crossing. Very good. Now there's also braiding. Okay, and the only difference in braiding between regular braiding and this G cross braiding is the fact that when you braided two anions together, it just flipped them. But when you braid two G graded anions together, or G or H graded anions together, it actually doesn't just flip them, but also introduces some sort of G crossing action on the anions. Okay, and that's sort of noted over here. Notice that again, if G equals 1, then you literally just get a flipping of anions, and this is just the usual braiding. Okay, good. So the final theorem for this talk is going to be that you have some category, which is G sec gamma 0, which is the category of G localized or of localized transportable endomorphisms, where localized means G localized, H localized for all group elements. This is actually a G crossed braided C star tensor category, and that's the theorem that we proved in our in the paper. And there's like some assumptions like existence of gap and blah blah blah. And sort of importantly, in all so this is the exact same as so let's say if no anions, then of course it's an SPT, because there's only like some sort of G action on like trivial anions. Turns out that G sec gamma 0 is isomorphic to the category WEC G omega. So that's basically that's the correct category that physicists describe, or that physicists use to describe SPTs, and our category reduces exactly to that SPT category. So that's very reassuring. And in fact, it's not the easiest thing to show, but we have shown it that even in anionic order, in topological order, there are some examples where the physicists' categories are exactly what our categories reduced down to as well. So it's all encouraging is sort of what I'm saying. Okay, so the final piece of our puzzle is the symmetry fractionalization, and literally, as you can see, only 2 more slides left. So stay with me, I suppose. If I have a G crossing on an object, then let's say I have some object, it's in G sec, meaning it's some symmetry defect, and I G crossed it, then as I sort of erased earlier, something in the H component is going to go into G at G inverse, something like that. Okay, but it's not necessary that it goes to the standard one. Okay, so if you have some sort of you have some standard list of objects, it's called skeletalization. Then you will have maybe some isomorphism that takes you from the G-crossed action on an object to some other object, which is the canonical object in that component, or one of the canonical objects in that component. And that isomorphism, let's call it V. Now, using this isomorphism, there's two ways to get to a canonical object starting from sort of double actions. So you have gamma G, gamma H acting on some object sigma in the category Gsec. The way you can do it is first you can like resolve this object and call it some canonical object sigma prime. And then you can resolve this object again and call it some other canonical object sigma double prime. Or you can just multiply these two things together, and they're just like usual conjugation by symmetry actions. So they have the usual group-like multiplication rules, and then you resolve this thing right here directly into sigma double prime. And the thing that relates the two is our symmetry fractionalization. It's that eta, that elusive eta, that tells you how to go from here to here. Okay, but this is very arcane. Okay, what the hell? Like I lost everything, right? Like I started off from such nice string operators. Now I have like completely sort of, right? I've completely dressed the structure up in endomorphisms and isomorphisms and blah blah blah. There's a category now. Nobody really knows what the basic sort of microscopics were. But here, sort of, I'm gonna start to come back to microscopics in the last two slides. So in BBCW, there was this like cartoon that they drew, which was like, okay, you have some anion, A1, A2, A3, A4, whatever, and there's some global anion corresponding to this distribution. And if you act on it with like this big symmetry everywhere, okay, then the symmetry is going to sort of fractionalize in such a way, it's gonna give you some sort of unitary action that's surrounding these anions, and it's also gonna like give you some anionic action itself. So you're gonna get some G action on the anions. So in this sort of whole analysis, to build back, the RG that they talked about, the complete symmetry action everywhere, is our gamma G. That's the G crossing. And this UG that they talk about, that sort of would be some unitary that's like localized over here, that actually is our isomorphism V0. That is, oh, sorry, I switched the symbols around or whatever. It's the isomorphism that tells you on how to go from a G crossed object to the canonical object in that same component. But okay, maybe this is not enough physics for you. You really, really just want like how to calculate it using microscopics. Well, I got you covered. How do you calculate this symmetry fractionalization? Well, what you do is you sort of choose representatives of your defects. So let's say you already know most things about your category. Let's say you know that, okay, there's going to be like these many defects and there's going to be these many anions, which is not so hard to determine if you're working with like with a microscopic theory or with a finite theory with like with a nice sort of commuting projector description like Levin-Wen and things like that. Okay, so let's say you know all of that. You know all of the symmetry defects. You also know all of the anions. Then how do you calculate the fractionalization using these? Well, it turns out it's very easy. So the complicated endomorphisms will now reduce to something really nice in such a finite lattice model. So UG box is the symmetry action on a restriction of the region. So let's say this is the right region. So you want to think of the box as like some very finite dimensional thing. FD is the correction. So this blue thing right here is the correction of the symmetry on some half infinite line, or like, going from here to over here. And then there is also some anion tacked on. Let's say some anion A. And now you send all of it to infinity. Send this to infinity, infinity, infinity. So the box nature of it disappears. You literally just have like, you have some green line over here, which is the domain wall. And then you have a blue and red line stretching off to infinity over here, which is the correction and the anion. Okay, well, you calculate your isomorphism by literally doing this. And sort of the way you would want to understand this is that you sort of act on this object, whatever this object was, this picture right here, correction plus anion object. You act on it with the symmetry. You act on it with beta g, and you will get some other object. You'll get some other weird object, but then you sort of just relate it to the canonical object. And in doing so, you'll get some phase. You'll probably get some phase or some local operator. And that local operator is only going to defer, or like is only going to be acting over here in this region right here, because that's the only region where it can realistically differ from the canonical object. And that VAG, using the previous formula, this formula right here, you can calculate what the symmetry fractionalization is. So, right. How to find it? You take some canonical thing, and then you act on it with a symmetry, and then you relate it back to the canonical things that you had. That'll give you some isomorphism. That gives you some symmetry fractionalization. Okay. And there's an algorithm to do so. So this is like a summary of what we've done. You can read through it. It's just summary of the talk and questions.
So can you say, like, these, if you take these morphisms and create new sectors with them, not going to be ground states, but are like the dynamics still unitarily implemented? And if so, is the spectrum something?
Great, yeah. Excellent question. So this new symmetry defect state is actually not a ground state of the original Hamiltonian, but you can define a new Hamiltonian that has that as a ground state, and then the dynamics are completely unitarily implementable for that new Hamiltonian. And the Hamiltonian is like literally, so, okay, maybe I should just, so if rho is in GSEC, gamma 0, then rho of H, where H was your previous Hamiltonian, is the new Hamiltonian, and then all the dynamics and everything are generated by this thing right here. Yeah.
And does it remain gapped and preserve all these nice properties? Nice. Okay.
Yeah, exactly. It's going to remain gapped. Everything's going to be really nice. And in fact, this actually shows a very beautiful result that we comment on in the paper, is that if H was commuting projector Hamiltonian, then rho H actually gives us a way to build commuting projector Hamiltonians corresponding to defects. So for every time you want a defect, let's say you know what the string operator for the defect looks like, perfect. You literally are able to go from your previous commuting projector Hamiltonian to a new one, which is powerful because in quantum computing, they actually really want stabilizer models, and commuting projections really help them in sort of defining these new codes which are able to implement more interesting things. And these symmetry defects actually have such an interpretation that these are actually Hadamard gates for the Toric code, and gives you like some way to construct codes that are able to change the location of your symmetry defect and things like that. Absolutely.
Actually, sorry, could you give more intuition for why rho of H works? I'm a little surprised because I'd imagine, locally the derivations should always look the same regardless of what representation you're in. So given that local rho of H,
Is that so? Not quite,
like
right? Because
locally,
locally,
all representations are unitarily equivalent.
right, but however, globally they're not. And
Right, but like
okay,
since
so
the
let's say
Hamiltonian is still made of local terms, and
right. So
yeah.
right. So let's say you make a new Hamiltonian H prime from some, let's say you go from H to H prime in a local way. Okay, let's say you just like you have some local operator like this that you're conjugating H with. Even though the dynamics are unitarily equivalent, they're still different. They're unitary equivalent, but the unitary is telling you how to go from one to the other. And this rho is not really doing anything on a global sense. It's really just like looking at it from a local sense. Like you're just sending this thing off to infinity, and that's all it's doing. It's not doing anything complicated. And then the dynamics should all be unitarily implementable, but now these dynamics are not going to be unitarily equivalent to the usual dynamics without the
Right.
symmetry defect, because of the fact that representations are globally different.
I see.
Yeah.
Thank you.
Yep.
Any further questions from our people on the record? Okay, well, hearing none for now, I'll stop the recording.